Okay, folks, for this screencast, we're going to do something called Broydens Method. It builds on Newton-Raphson and the Secant Method. So what I'm going to do is just go over the Newton's method real quick. Newton's method, and then the Secant method, and then we'll go over Broyden's. So we're going to fly through Newton and Secant. I already have videos on those two. First, let's evaluate the function and see what we're working with. So basically, I got an email, and so the function that I got was function out equals f of x, and out equals x1 plus 2 times x2 minus 2, x1 squared plus 4 times x2 squared minus 4. And the input x is going to be a vector. It's going to be a 2 by 2. And this is our function that we are trying to solve for. And basically what we want to know is, solve for x such that f of x equals 0. Now, when you're evaluating functions like this, it is possible that there is no solution, but we're going to evaluate it anyway and see if there is perhaps a solution. So I'm going to do function Broydens Method up here. Remember, when you have a function and a function, you need a function header at the top. So I'm going to make x1 go from -2 to 2, and x2 is, I'm just going to make the same thing as x1. I'm going to mesh that using mesh grid, x2 comma x1. And then I'm going to pre-allocate ZZ1 and ZZ2. And then what I'm going to do is I'm going to do a double for loop. And I'm going to loop through x2 and x1. And then basically I'm going to say, okay, the xij is x1 of idx, x2 of jdx. And then I'm going to say out is f of xij. So I'm actually going to evaluate the function at that current coordinate. And then I'm going to put it into here, into my two matrices, where the first row of the output is the first function, ZZ1, and the second row of the output is the second function. And then I'm going to make a figure, and I'm going to mesh xx1, xx2, zz1, hold on, and then I'm going to mesh xx1. And I'm going to surf the second one, see what happens, and run that. Okay, so there we go. So here is our here are our two functions. It looks like they both intersect in this sort of circle here. The question is do they both cross 0 at the same point? And it looks like they might around here. I'm not entirely sure where. I mean, I guess we're gonna find out and see if this. I think I've done this before. I think this will converge. But here we go. So how do you do Newton's method? So for Newton's method, you need an initial guess. So I'm just going to do 1, 2, just because I don't exactly know where it is. I'm going to compute my error, and my error is essentially going to be, let's see, I'm going to make an error function out equals error of x. And so what I'm going to do is I'm going to say, okay, first, I'm going to do out error. First, evaluate f of x, and then I'm going to say that my out error is equal to out 1 squared plus out 2 squared, like that. And then I'm going to say error is, okay, so then I'm going to just say while, and I'm just going to call this x. I don't really need, I'm going to say while error of x, and I don't need to do absolute value because there's squareds here, so there's no problem. While error of x is greater than 1e minus 2, do the Newton-Raphson. So in scalar coordinates, you have x next equals x now minus f of x divided by f prime of x. Unfortunately, since f is a vector function, we can't do that. So we have to do x next equals x now minus f prime to the minus 1 times f of x. Now f prime is a 2 by 2. Since f of x is a 2 by 1, the derivative is a 2 by 2. So this is actually called the Jacobian. So what we want to do is we want to make a function that computes the Jacobian. So I'm going to just say j of x. So again, x1 is x of 1, x2 is x of 2. Oop. So what we need to do is we need to say out is going to equal this function, and I'm going to take a derivative with respect to x1. So I'm going to get this function, take a derivative with respect to x1, so I'm going to get 1, 0, 0, so it's just going to be 1. And then I need to take a derivative of this function with respect to x2, and so that's going to give me 2. Then I get the second row. The second row is going to be the derivative of this guy with respect to x1, so I'm going to get 2 times x1 plus 0, 2 times x1. And then I'm going to take this function, take a derivative with respect to x2, so I'm going to get 8 times x2. 8 times x2. And there's my Jacobian. So now I can say, and in the interest of Broyden's method, I'm going to say S equals negative inverse of j of x times f of x. And then I'm going to say x equals x plus s. And if we're lucky, I'm going to put this over here. Things never work on the first try, but if we're lucky, oh, look at that, it worked. It converged very, very quickly. So let's actually do, let's get rid of the semicolons, and let's make this while minus 10. Let's see, let's let it iterate a lot. And then let's do different initial conditions. And then let's say display solution equals display x, and then display error equals, and then I'm going to say display error of x. Alright, so there we go. So the solution looks like it is 0, 1, and the error is that. What I'm also curious is display f of x equals, and then display f of x, like that. Let's run that. So yeah, so there you go. So let's just evaluate this, just in our head here. So if I plug in 0, 1, so I'm going to get 0 plus 2 minus 2, that's 0. And then I'm going to get 0 plus 4 times 1 squared, which is 4 minus 4 is 1. Exactly. So we got it. And then if we relax our coordinates here, my solution's not quite there yet, but it's close. I mean, there's my error there. But if you do minus 10, it iterates a lot more. Okay. So now let's do let's see what my time is here. So that was 8 minutes for Newton's method. So, all right, so let's move along here. So secant method. So the difference between secant method and Newton's method is that you basically do the same thing. You want to solve, copy, and paste. But the problem is that you don't have j of x. You don't know what the derivative is. So you have j numerical. And what you want to do is a first order derivative. And so instead of explicitly knowing function out equals j numerical of x, instead of explicitly knowing what the derivative is, so this is the function, here's the derivative. Since I don't know what it is, I need to figure out what it is using first order derivative. So technically it's df1 with respect to dx, dx1, and then df2 with respect to dx1. I'm sorry, no, it's df1 with respect to dx. Do I have this backwards? Hold on, give me 1 second. I'm losing my mind here. Okay, sorry about that. I have this right. So f of x is f1 semicolon f2. So out is df1 dx1 and then df1 dx2 and then semicolon df1 df2 dx1 df1 df2 dx2. Okay, so if we write that in vector notation, it'll be df, right, dx1 space df dx2. So basically the first column is df dx1 and then the second column is df dx2. So if we approximate this using first order derivative, basically the first column out of all comma 1 equals the function evaluated at x plus dx minus the function evaluated at x minus dx all over dx. Now dx is going to be 1e negative 2, 0. It's a small infinitesimal change along x1. And then the second column out of all comma 2 is going to be the function of out at x plus, and here maybe I should do this, dx1, 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 and that way I don't confuse you. dx2 is 0, 1e negative 2, dx2 minus f of x plus dx2 over dx2. And I think that'll be it. You probably want to pre-allocate and say out is going to equal zeros 2 comma 2, just so we have that. And so that will approximate our derivative. And so if I run this, let's do secant solution, Newton solution. If I run this, hopefully this worked. Oh, blast, didn't work. What's happening here? This is a column. Yeah, I need to. Oh, you can't divide. Here, let's do dx here like this, dx1 like that, except I'm going to put a del here. And then I'm going to make del equal to 1e minus 2, and then you have to divide by del. You can't divide by a vector. There you go. So you put del in the right spot, and then and I need parentheses as well. Good thing I caught that. And then you divide by the scalar del here. Okay. Didn't like it at all. Maybe my del isn't big enough. What about 6? No. Give me 1 second to see if I can figure. Oh, this is never on. This is central differencing, right? This is central differencing. So that means this needs to be 2 times del, and this needs to be 2 times del. Blast. Okay, give me 1 second. Okay, folks, I'm not sure if you caught this, but there's a plus here and a minus here. So you do your forward function call, your backward function call. Here you do your forward function call, and then here I did another forward function call. So just need to change that to a minus, and there we go. So let me get rid of all of these semicolons here. When I was debugging offline, I got rid of this here. There we go. So let's see. So the solution, Newton solution is here. The secant solution is here. The error is pretty much the same. The function evaluation is pretty much the same. They both converge to 0, 1, which is good. So the Newton and the secant method both did what they could. Okay, so Broydens method. So finally, so let's bring up Broydens method. So I found Broydens method online, and basically it's like this. Can I make this bigger? How does this work? Google Slides. How do I do you? Okay, well, you're just going to have to zoom in and read that. So what we're going to do is we're literally going to just copy this entire thing. Copy, paste. We're going to get rid of secant. I'm going to use the exact same initial conditions. Did I use the same? Oh, I used 2, 2 there. 2, 2. Maybe that's why I got different results, 2, 2. And now basically we're just going to follow this. So if you look, you need an initial guess for the Jacobian. So you have a b, and you have an initial guess. So I don't actually know what the Jacobian is, so I'm just going to make it the identity, because I have no idea what the Jacobian is. I don't have any idea whatsoever. So then what I'm going to do is, I'm going to solve for this. I'm going to say invert b times f is going to give me s. And then I'm going to say x equals x plus s. And then I'm going to evaluate y, which is f of... Okay, and it looks like I need to do this first. So I actually need like a xk1, or an x1, so I can get the difference between the two. So I'm going to get y is f of x1 minus f of x. And then this is the Broyden part, where you recompute and update the approximation of b. And so b equals b plus y minus b times s transpose all over s transpose times s. Now, I need to put an if statement in here and say if s transpose times s, I'm just going to throw an absolute value in here, is less than 1e negative 2, is greater than 1e 2. Do this, otherwise don't. Okay, so that's Broyden's method. I don't know how to derive it or where it comes from, but I'm just putting it in here because that's what I'm doing. And then I'm going to replace this with Broyden solution, and let's see if it converges. Oop, definitely did not. It's just going. So let's see. Probably instead of doing a while loop, we probably just want to do a for loop. Oh, I know what happened. This is pretty easy. I never updated x1, so after I evaluate y, I need to say x equals x1. That way I can actually reevaluate it. There we go. Sweet. So there's Broyden solution 0, 1. So it got it. No problem. So that's actually pretty awesome. I'm curious. Let's display. So let's get rid of all the errors, because we know they're all the same. Okay, so there's all the solutions. They all converge to pretty much the same thing. But what I'm curious about is, let's display Jacobian, numerical, and Broyden. So I'm going to display j of x. I'm going to display j numerical of x. I'm going to display b. And I'm curious to see what they are. So let's see. So it looks like I need to do like a space or something. So there's the Jacobian actual 1, 2, that 8. It looks like the secant method converged to the exact same thing. So the numerical, wow, the numerical is the same? That's crazy. I mean, what if I do -2? Yeah, something fishy is happening here. There's no way that's the same. What if I made it like 10? Okay, hold on. Something fishy is happening here. Unless it's I'm doing central differencing on a pretty simple function here. I mean, it might just be completely accurate, but I'm not entirely sure. I'm not entirely convinced, because if you look at Broyden's matrix is like totally off. I mean, 1, 2, that's right, but -44, -25 is way off. I'm surprised that this converged, to be honest. But it is what it is. I might tinker with it a little bit more, but hopefully that will help you out with Broyden's method. Good luck. Hey folks, so I'm back for a sec. So instead of doing central differencing, I did forward differencing here, and I used my del of 100. And so what I realized is that if you look at the difference between the Jacobian actual and numerical, because this function is linear, it doesn't matter how big del is. And then this is a quadratic, so if you use central differencing on quadratics, it's exactly the same. But if you do forward differencing, it's completely off. And then it looks like for some reason the whole thing converges, even if the entire second row is completely wrong, which is kind of crazy that it works. But I mean, that's just kind of the beauty of numerical optimization. But yeah, there you go. Good luck.